it's not clear to me what changes we can make and still have the things I'm about to say become still true. But I can't rule out that there are sort of changes that allow it. Great, other questions? Okay, so these are sort of the claims and the outline of my talk. The goal, or the lecture, the goal now will be to really unpack what I mean by these in detail and to understand why they imply each other. So this is sort of the punchline. And now our goal is to understand. So en route to that understanding, the first thing that I should tell you is I should tell you what a matrix product state is. Because that will be key to understanding the structure of these excitations. So sort of show by hands who knows what a matrix product state is? Some non-trivial fraction, but not everyone. So I apologize for those of you who know this already. It'll be good review. So a matrix product state is just a wave function. And in fact, it's going to be a wave function that describes every excitation. And there are lots of ways you can define a wave function, but one pedantic way is just to say a wave function is something that eats a configuration and spits out a number. So all I'm going to do for you now is I'm going to describe for you the rule by which matrix product states eat configurations and spit out numbers. And in particular, the configurations will be spin configurations in the SC basis. So we have a certain number of sites. Let's say it's 4 sites. And for each of these 4 sites, we're going to have 2 matrices. There's going to be a matrix that's going to be designated as the spin-up matrix, and there's going to be a matrix that's designated as the spin-down matrix. So in this case, we have 8 matrices. And now what we need is we need some rule where I tell you what the configuration is, and then we figure out how these matrices combine to give us a number. So what we're going to do, imagine that the configuration is spin up, spin down, spin down. Then what we should do is the following. We should multiply the spin-up matrix on site 1 by the spin-up matrix on site 2, by the spin-down matrix on site 3, by the spin-down matrix on site 4, and then we should take a trace, and that will give us a number. There's another variant of this where the matrices on site 1 and 4 instead of matrices are vectors, so that we don't have to take the trace at the end of the day. That distinction won't matter much to us for this talk. So this is just some rule. You essentially have 2 matrices. You take a configuration, you multiply the respective matrices, that gives you a matrix back. You take the trace, that gives you a number. Okay, so now I have defined for you what a matrix product state is. It is a wave function, and it works via this particular rule. Any particular questions about that?
Why is that a good representation of the wave function for a steady state?
That's not at all obvious yet. I mean, generically, if not, we'll see why it is for MBL in a little while. Other question?
I was going to ask, what is the field of their matrices over, but I think the answer is just going to be the quantum numbers. Right?
Well, these matrices will just, to 0th order, these matrices have numbers in them.
Yeah.
Just numbers, period. One can be more sophisticated and have blocks of matrices that can store quantum numbers and things, but none of that is important. There are just numbers in here, there's some size, big D by big D, and they just have D squared numbers, period. Yes?
Why trace and not determinant, or 5 times the trace?
It's a rule. One could, of course, write many other rules. One nice thing about this rule is it turns out that one is that all wave functions can be decomposed into this way. It's just that some wave functions require bigger matrices than others. Another nice thing about this rule is that low entanglement states get decomposed in this way, and it works well. But of course, one could write a wave function with your favorite rule. It just happens not to be this one. In some sense, it's just a definition.
So when you take the trace, you just get a number, right?
Yeah. A wave function, right? It's just an object. It eats some configuration, up, down, down, and spits out some number, 0.27. Right? And so I've just pedantically defined for you this wave function by telling you what that rule is.
Is there any connection with the representation theory?
No.
Just It's a different story, but just reminds me of it.
Okay, I am not aware of any such connection. I mean, there may be, but I'm not aware of any such connection. Great, so there's a notation for this that we'll kind of liberally use. The notation is as follows. This is a universal notation for this. So these boxes are matrices. They eat a configuration. That's the leg sticking out of the bottom, up, up, down, down. And then, okay, this box is a matrix. Here we go. A matrix that has an alpha and a beta. And when you have two boxes sitting next to each other, that means to sum over the beta. So this is essentially some vector alpha times m alpha beta times m tilde beta gamma times v of gamma. Gamma is shared here because they share the same line. Beta is shared here because they share the same line. So this is just a graphical representation, a graphical notation for taking a product of matrices once you fix whether this is up, up, down, down. Everyone reasonably happy with this notation? Yes.
So it's like a tensor product.
Yes, this is a tensor product. So this here is actually a 3 tensor. And then when I fix this spin, this is now sort of erased because I fixed that spin. And now we have a 2 tensor, that's a matrix. And if I multiply 2 matrices, I contract over this interior beta, and then I get something with 2 sticks sticking out still, that's still a matrix. So this just lets us like play with tensor notation without actually like writing out all sorts of complicated tensor notation. Right? So this is just a universal notation for matrix product state. It will come in useful later.
Sorry,
Yes.
what is V alpha? Is that a vector or is that a matrix?
Yeah, that's a vector. Now if I stuck something out here, if I did this, then this would be a matrix V I alpha, and this would be a matrix V gamma I, and I sum over I. So I said over here, there are 2 versions of this. One is where you trace at the end of the day. One is where the edges are vectors. And notation-wise, that matters whether I put a line between them or whether I just like leave that line out. Yes?
So the matrix product state is the tensor product of each matrices, or is that the is it? So my question is it a tensor product or is it a matrix product?
Well, it's just both, depending on how you want to think about it. So if I just write these boxes out, this is the matrix product state. What this tells you is this tells you that it's either a bunch of, say, 3 tensors in the middle here, or once I condition on the configuration, which gets eaten at the bottom, it's then a bunch of matrices in the middle here. You can multiply that. So that's why it's called a matrix product state. People sort of intuitively think this leg here is special. This leg here is the thing that's eating the actual physical configuration. And then you contract the rest of it. Yes?
Are they Pauling matrices?
No, just matrices.
Or what decides what matrices go on each box?
Nothing decides. I put numbers in each of these boxes, and that forms a matrix product state. And I put different numbers in these matrices, and it's a different matrix product state.
They're not like eigenstates.
Not eigenstates. We're going to find out that we can represent eigenstates in this way. But at the moment, I'm just defining a class of wave functions for you. It's like defining a Slater determinant. A Slater determinant has some single particle orbitals in it. You could ask what single particle orbitals go in there. Well, any single particle orbitals can be put in there. It might be that certain choices are good for certain problems. Great. Other questions? Okay, so now we've defined what a matrix product state is. And now we can understand this claim that I've made here about the eigenstates in a little tiny bit more detail. So I have, for my MBL system, I have some ground state. It's a Hamiltonian, it has a ground state. And I can represent that ground state by a matrix product state. And so what I mean by that is that for each site, I have 2 matrices. a matrix for spin up, and a matrix for spin down. And for site 2, I also have two matrices, a matrix for spin up, and a matrix for spin down, et cetera, et cetera. Now, we'll see in a minute that there's some gauge freedom in these matrices, that I can change these matrices but not actually change the wave function, i.e. for every configuration it gives me back the same number. So let's just say I've chosen a very special form of these matrices for the ground state. Okay, now I will use notation and say, look, I'm just going to like collapse these two matrices into sort of G1 bar and G2 bar. So this is just notation. G1 bar are the two matrices up and down for site 1. And now what I'm telling you is that there exists so there are n matrices here. G1 bar to Gn bar. There exists another set of n matrices, E1 bar to En bar, where again, by abuse of notation, each of these is actually a spin up and a spin down matrix per site. And now the claim is that to form any of the excited states, this is just another set of matrices. It doesn't necessarily correspond to anything at the moment. To form an excited state, I pick, say, site 1 is the G, site 2 is the E, site 3 is the E, site 4 is the G. I pick any combinatorial combination of the G matrices, the G pairs of matrices, and the E pairs of matrices. And that gives me an excited state. Okay, so that's really what I mean by claim 1 here, in sort of a little bit of gory detail. So there are 2 to the n of these, right? At each site, I either get to pick the G or the E matrix. There are 2 to the n excitations.
How do you choose the E's and the G's? Like, what's the difference between them?
At the moment, I'm just telling you there exists special G's and E's such that this is true. And in a little bit, we'll see where they came from. In fact, they come from, they're sort of extracted from the quantum circuit, is the short answer. And we'll see why that is in a minute. But at the moment, I'm just telling you that this is sort of an existent proof. And one second. In addition, one of the special things, or sort of the special thing about many-body localization, is that these matrices sizes will not grow as my system gets bigger. So for a given disorder strength 6, maybe the matrices are of size 1,000 by 1,000, no matter how big I make my system. Again, in 2 minutes, I will attenuate that with what do we mean, because we have a disordered average. Before I do that, we had some question. Yes?
They were related by a transformation?
No, they're not. There are just some G matrices, and there are some E matrices. There are 4 n squared, unrelated, uncorrelated numbers here.
Okay.
If I give you those numbers, you now have information to build the entire spectrum. Yeah, so let's build an excited state. I take, so I'm gonna build a matrix product state. A matrix product state needs 2 matrices per site. For site 1, I'll take the 2 G1 matrices. For site 2, I'll take the E2 matrices. For site 3, I'll take the E3. For site 4, I'll take the G4. So for each site, I get to pick either G or E. So there's 2 to the n of choices. And the spectrum has 2 to the n states in it. So it's plausible here that I can describe the entire spectrum this way. In fact, I argue that it's true. Okay, good. Questions? Yes.
So, what is E matrix? Is that also ground state?
It is not. This is the ground state. This is not the ground state. It is, in fact, some excitation, given what I've told you, because you can just pick all the E matrices, and that gives you an excitation. But it might, I don't know what excitation it is. It might be the highest excited state, but it might also be like 8,032,000 excitation. It is some excitation. And it's not trivial for how you get these E matrices. Actually, it's not trivial to how you get the G matrices even, because there's some gauge freedom running around. The moment I'm telling you sort of an existence proof. There exist such choices of these G's and E matrices, such that I get to build the whole spectrum. Yes?
How do you get the number for n squared?
Good. So there are 2 n matrices here. There are 2, okay, that was a stupid word. There are 2 n matrices here. So that's 4 n matrices, and then each of them has d squared numbers in it. Second. Thank you. 4 n matrices, d squared numbers per matrix. Good. Any other questions?
How do you define the quantum average for this kind of system? I'm not saying for particular free function in terms of MPS. I'm saying for this manually localize the phase, how to define a quantum average? How do you compute any quantum average for an operation? Because you have a bunch of wave functions instead of one, right?
Well, no, I have a wave function per excited state.
Yes, but how do you define the quantum average?
For any excited state, I just have a wave function, right? So I can define a quantum average.
So you only compute the quantum average for particular wave function.
At the moment, yes. Okay, other questions? So we should just pause for a moment and realize that this is sort of phenomenal in the sense that naively you might think, look, for a typical non-MBL system, I have 2 to the n excited states, and each of them requires something like 2 to the n numbers to describe. So generically, if I wanted to describe an entire spectrum, I should have to give you 2 to the 2n numbers. And now what I'm telling you is that to describe the entire spectrum, I essentially give you a linear number of numbers. And this gives you the spectrum in a very kind of a compact way, but also a way where like you can compute things. This explicitly tells you like what the wave function is, and then you can compute any property of the excited state you want. So this really is sort of some statement about the compactness of the MPL phase that's really special. Of course, that was true over here in this product state. Here I gave you like n numbers, who was up and who was down, and that also specified the whole spectrum. But this was a non-interacting system, and over there it looks like a complicated interacting system. Okay, great.
But,
Yes?
sorry, even if those things are interacting, if I know all of them, oh, all right.
I mean, normally I really need 2 to the 2n numbers to describe the whole spectrum.
So in this case, are there degeneracies?
Probably not. I mean, not generically. In a finite system, not generically.
But there seems to be a loss of information.
No, it just means that somehow there's a really compact, beautiful representation. There's no loss of information, it's just a compact representation.
Sorry, what's D?
What? D is the size of these matrices, and my claim is that it's fixed. It doesn't get bigger as your system gets bigger. Attenuated in one moment about the correct way of doing that average. Yes?
Maybe you can talk about this later, but I don't see why that reports here. Why it wouldn't work mobility edge? If you can talk about it later, then let's not discuss it now.
Okay, so the short answer to that is as follows. Matrix product states with fixed bond dimension only capture low entanglement things. And if you have a mobility edge, there are going to be some states that are ergodic. Those states are going to have high entanglement, and therefore there's no way you can describe it with so few numbers.
Even if they are short range entangled?
If their entanglement is volume law, which generically will be outside the mobility edge, then generically in this representation you need an exponential number of numbers. And here we, for one state, which is the not surprising thing, and here we've described the whole spectrum in a linear number of numbers. Great. Other questions? Okay, so now let me be a little bit more careful about what I mean when I say this size of this matrix doesn't grow with D, because I'm lying a tiny bit. So let's recall what we're doing. We're doing a disordered problem, which is to say that I have some Hamiltonian over here in the MBL phase, and what I'm doing for each h sub I is I'm choosing some number in this top hat distribution. And of course, it might be that for a particular realization, I get unlucky and I choose the number 2.3 for all my sites. And if I do that, of course, that system can't be a special system. I mean, there's no disorder in that system, right? It's like choosing 0 for all the sites. That system can't have this special property that there is some compact, representation of it. So what I would have liked to say is I would have liked to say, look, what I did is I just averaged the disorder, averaged the bond dimension D over all the disorder. Okay, but if I do that, I'm in trouble because occasionally I get a rare non-disordered system where this number is exponentially large, and that screws up my average.